So, hello, my name is Archit, and today we're going to go over the AP Physics C 2002 number 2 FRQ. And let's start off with the problem. And FRQ 2 asks us we're given a rubber ball of mass m is dropped from a cliff. And as the ball falls, it is subject to air drag. The drag force on the ball has a magnitude bu squared, where b is a constant drag coefficient and u is the instantaneous speed of the ball. The drag coefficient b is directly proportional to the cross-sectional area of the ball and the density of the air and does not depend on the mass of the ball. As the ball falls, its speed approaches a constant value called the terminal speed. Okay, let's move on to part A. On the figure below, draw and label all the forces on the ball at some instant before it reaches terminal speed. So we already know one force, which is gravity, right? So gravity is going to work on the ball, and F equals ma. And in this case, the acceleration value is gravity, so force of gravity is mg. And we're given that the drag force is negative bv squared. So that's gonna oppose the motion of gravity. So as the ball speeds up, we know the drag force becomes larger until the ball reaches terminal velocity. So at the point where the ball reaches terminal velocity and doesn't speed up, we know the forces have to be balanced. So in this case, we want both areas to be of equal magnitude and in opposing direction. So we have drag force in the opposite direction with equal magnitude as mg. So let's move on to part B. Say whether the magnitude of the acceleration of the ball of mass m increases, decreases, or remains the same as the ball approaches terminal speed. So as seen in the previous free body diagram, we have two forces mg and negative bv squared. And as you can see in the diagram over here, we have we have the forces at different time periods. So as soon as the ball is dropped, there's no drag force, and the only force is mg. So that's when acceleration's the maximum because the net force is the highest over there. But as time approaches and as we get closer to that terminal velocity, we notice that the drag force also becomes bigger. And since that terminal velocity, the drag force cancels out with mg, we know that acceleration during that time is zero. So the sum of the forces is zero. The net force is zero. So as time increases and as the ball gets closer to terminal velocity, we know that the magnitude of acceleration decreases since the forces cancel out each other. Okay, let's move on to part C. Write but do not solve a differential equation for the instantaneous speed u of the ball in terms of the time t, the given quantities, and fundamental constants. So F equals mg, the force of gravity, minus bv squared, drag force. And we know F equals mass times acceleration, force equals mass times acceleration, so let's write that down. Ma equals mg minus bv squared, and acceleration is also the derivative of time, right? So we can replace A for m times dv dt equals mg minus bv squared. And what we want is to solve for dv dt, right? So let's divide both sides by m. M goes to the other side. Then we do some, so dv dt equals mg minus bv squared over m. And then once we do some simplification, we get dv dt equals g minus bv squared over m. That's how we get. Okay, so let's move on to part D. Determine the terminal speed ut in terms of the given quantities and fundamental constants. So we know what terminal speed, as we've observed before, the force of gravity equals drag force. So we're here. And we want to solve for velocity, right? And F force of gravity is mg, and we know for the drag force is bv squared. So we want to solve for velocity. So let's try to simplify this equation and move constants to the other side. Velocity squared equals mg. Divide both sides by b. We get v squared equals mg over b, and then let's take the square root of both sides to isolate velocity. We get velocity equals the square root of mg over b. Finally, let's move on to part E. Determine the energy dissipated by the drag force during the fall if the ball is released at height h and reaches terminal speed before hitting the ground in terms of the given quantities and fundamental constants. So we know potential energy is mgh and kinetic energy is half mv squared. So total energy is mgh minus half mv squared, since as the ball loses potential energy, it gains kinetic energy. And we also know that the velocity is the same thing as square root of mg over b, which we got from part D. So let's plug it in. Let's replace square root of mg over b into velocity and see what we get. So we have delta E or energy, change in energy, equals mgh minus half m times, this is where we replace velocity, right? So we have times the square root of mg over b squared. And once we do some simplification, we get delta E equals mgh minus half m squared g over b. And then finally, as we, oops, my bad. Finally, as we solve this, we get delta E equals mg h minus half m over b. That's when you fully simplify it, and I think we're done. So yeah, don't forget to smash the like button, smash it, and smash the subscribe button, smash it. Do I end this, bro?